And we're back at it. Again, we are doing calculus CLEP exam questions from the sample exams that were found online at these addresses. Link in the description. We're still with this one. We left off at number 26. And that is asking, what is the area of the region in the first quadrant, meaning the upper right of the graph where everything is positive, that is bounded by the line y equals 6x and the parabola y equals 3x squared. So just to give you a little idea of what that probably looks like, you have some kind of parabola and some kind of line. This would be y equals 3x squared. This would be y equals 6x. And there is going to be some region in between those two functions there. And they're asking us, what do we think that area there is? And so the primary trick here, anytime you want to know the area between two functions, well, by using the definite integral, we can find the area below this function, and we can find the area below this function. So if we have that area and that area, then all we have to do is take this one and subtract this one, and that bit in the middle is what's left. So we have to figure out a few things here. First of all, we know that, well, we need to find out what our bounds are. So we know that one of them is the origin, because at x equals 0 and x equals 0, y equals 0. So you're going to have your first bound at x equals 0. But what is that other boundary going to be at what x value? So we're asking, where is 3x squared equal to 6x? And we can just shuffle a few things around. Did I do that correctly? Yeah. So the easiest way to do that is to bring this x over here and that 3 over there. X squared divided by x equals 6 divided by 3. X squared divided by x is an x by itself, and 6 over 3 is 2. So we know our bounds is x equals 0 and x equals 2. So what we want overall is the definite integral from 0 to 2 of the upper function 6x minus definite integral with the same bounds 0 to 2 of the lower function, which is that 3x squared. So for definite integrals, we have to integrate, of course, opposite of the derivative. We're going to keep those bounds. So we say, what do we take the derivative of to get to 6x? Simple power rule, we know that we subtracted 1 from the exponent, so we're going to have something with an x squared. And to get there, we brought a 2 down, so we had to multiply 2 by something to get 6, and that would have been 3. And then keeping our bounds, here we have 6 squared, so we know that we subtracted 1 from something to get to the 2, So we would have started out with an x cubed, and we would have brought that 3 down to make that 3, so it is just x cubed by itself. And so this is what we do with definite integrals. To find the area under the curve, you have to know how to do this. And what we do is we plug in the upper bound into the x, and then we subtract the lower bound, the upper bound minus that with the lower bound. And then we need to do the other one as well. So the upper bound, 2 to the third, minus, plug in the lower bound, 0 to the third. And we're just going to run through and simplify things. 2 squared is 4. 0 squared is 0. All subtracting 2 to the third. 2 times 2 times 2 is 8. Minus 0. That's going to be 12. Minus 0. Minus 8 minus 0. And all that ends up being 12 minus 8, or just 4. And this is, again, no multiple choice. You just have to come up with the number, which is why the numbers are nice enough. No nasty numbers, all integers that you can work with. You fill in 4, and that is the answer. So next one here, number 27. And it just says, let f be a differentiable function. Differentiable just meaning you could take the derivative of it if you wanted to, which means it's something neat and tidy, not something crazy messy. Defined on the closed interval a to b, which just means that we're only concerned with what the graph looks like between some number a and some number b. And it says let c be a point in the open interval ab. What is that telling us? It is telling us that c is between a and b. C is in the middle. In fact, let's write down what we know. Telling you that c is between a and b. So such that the derivative of the function at c equals 0, which means the slope at that point c, the slope of the function is 0, where x equals c, which means it is probably a minima or a maxima, or maybe not, but we'll find out, I think. And it's also telling us that the derivative of the function is greater than 0, meaning we have a positive derivative, which means a positive slope. We have an increasing slope where for values between a and c. So the slope is positive value between a and c, and then the derivative for x's are less than 0. It is a negative value between c and b. So the slope is negative between c and b, and that tells us that C is a maximum because what it's telling us, here's A, here's B, here's C. The slope between A and C is positive, it is increasing, and the slope between C and B is negative, it is decreasing. So we know that we have a maxima where x equals C. So, which of these statements must be true? So option A, it's positing that the function where x equals C is equal to 0. And we don't know that. We just know it's a maxima. We don't know how high or how far above or below the x-axis it is. We haven't been given that information, so we know it's not that. It's asking, is the second derivative at C equals 0? Meaning, is it an inflection point? Do we know if the rate of change of the slope is changing there? And we don't know that at all. We've not been given any kind of information from which we might say that. So saying that the function at the value x equals C is a maximum value for the function between those two values, and we pretty much already said that's what it is. So we think it's that, but let's just check further. The next one posits, is it an absolute minimum value? So if this had been flipped the other way, but it's not, we know it's increasing and then decreasing, so it's definitely not that one. And then option E is asking, what if the graph has an inflection point at x equals C? And that's literally saying the same thing as selection B, which we said that, maybe it is, maybe it isn't. We haven't given enough information to determine that, so we can't say that it must be true, but C must be true. We did determine that. So then, number 28. The function f is continuous on the open interval, so we're going from negative pi to pi. Trig again. Don't we love trig? For the function f equals cosine of x minus 1 over x times the sine of x when x is not equal 0, because you get a divide by 0 error there. But what is the value of f equals 0? So the trick here, this is a limit question without coming right out and saying limit. Basically asking, what is the limit as x approaches 0? And why that is because it's saying it's continuous. So this is one of those composite things where if they just gave you the function, they would say it is all of this where x is not 0, and then say at x equals 0, it's some other thing, filling in that gap. And we had a question earlier where the fill in the gap actually missed the function. It was below where it should have been. But because this is telling us straight out it is continuous, that means that the given value at the x equals 0 would most definitely plug in that gap that is left by the divide by 0 problem. So if we find the limit, then we know what number would be being used to fill in that gap. And that's basically what it's asking, is what fills in that gap to make the graph continuous, where it can't be continuous if it was just this by itself, because of the divide by zero error. So this is more goofy trig stuff. We just kind of got to finagle it, because if you gotta, again, remember your unit circle, where the cosine is x and the sine is the y. So at the angle of 0 here, cosine of 0, x is 1, and the sine of 0 is 0. But now we want to know, it's a limit question, so we're interested in what does it look like just a little bit to the left and just a little bit to the right, so that we can figure out where they're probably going to meet. So cosines near 0 are going to be pretty close to 1, and a sine near 0 is going to be pretty close to 0. So that function again, cosine of x minus 1 for x sine of x. And what can we say about this? Well, the cosine of x near 0 is going to be something close to 1, minus 1. So it's going to be some small negative number. And then x again is near 0, and the sine of near 0 is also near 0. So it's going to be two numbers, two very small numbers, and the little trick here is they're either going to be both positive or both negative, because if we're near 0 in this direction, you have a positive y value, but if we're near 0 in this direction, in the negative direction, you have a negative y value. So it's either going to be a very small positive number and a very small positive number, or a very small negative number and a very small negative number. So either way, if they're negatives, the negatives cancel out. So either way, you're getting a very small positive number. And then the other trick from here is that this is actually two of them. They're being multiplied together. So we can kind of say it's two of them, whereas this one it's a subtraction. So you're basically having a small negative number and a small positive number, and we're saying small numbers. So one small number over another small number is going to end up being pretty close to 1. You're just talking very small numbers. So let's just approximate negative 1 over 2 times 1, and that ends up being negative half. And that's just tricky limit things where you're just going to have to say, yeah, it's going to be sort of near that, and just try to extrapolate, what's that likely to look at, what that's likely to look like. when you can't b equals negative, option B, negative half, when you can't punch it into a calculator. Of course, if you can punch it into a calculator and run the graph, you can just look at it, but this is the non-calculator section of the exam, so we have to do it the hard way and just kind of logic it out. And there does seem to be, at least a good handful of these kind of limit questions, so helps to be comfortable with what's going on there. So 29, we are given, we have some function g for which if x equals 20, the y value of the function is 0. So at g of 20, the whole thing comes to 0. And then the derivative of the g function is positive, meaning it is a positive slope for all values of t, meaning the slope is increasing for the entire function. We just know it's always going from small to large, or going up, increasing. So it also tells us that g is differentiable. Again, that just means that nothing goofy is going on. It's something you can take the derivative of using the normal rules. Satisfies those conditions. And let f be the function. Basically, f is the definite integral from 0 to some upper boundary they're calling x. So which of the following must be true? So we're just going to picture this out a little bit on a graph. It is some graph that's increasing. It might be a straight line, might not be a straight line. We're just going to go with a straight line for simplicity. And at the x value of 20, the y is 0. So it's doing this. It's because we know the slope is increasing, we know it's going to be below the x-axis over here and above the x-axis over here, because it's crossing the x-axis, y equals 0, at the x equals 20. So which of the following must be true? It's giving us some options here. First of all, f has a local minimum at x equals 20 or a local maximum at x equals 20. Well, we know that it's always increasing, so there are no minimums, there are no maximums. It's just continuously going up. So we can pretty safely rule those out. And no, I spoke too soon. Let's get a blank page there, because remember, we're not being asked about the function g. This is g. We're being asked about f, which is the definite integral from 0 to some x. So here's 0, and x is somewhere. We're being asked about the definite integral, so we're being asked about the area from 0 to somewhere. Might be here, might be over here, might be up to here if that x is greater than 20. So what can we say quickly about that? Obviously, if that x, if the upper bound of the definite integral is less than 20, if it's over here, the whole thing is going to be negative because it's below the x-axis. When you're taking a definite integral, everything below is negative and everything above is positive. So if that bound is here, it is all negative. But if the bound is up here, then you're starting to get into the positive again. So actually, it does turn out to be the first one. At x equals 20, you think as you go along with that upper bound of the definite integral, if you start at 0 and you keep going this way, you're getting increasingly negative because you have an increasing amount of negative area until you hit x equals 20, and then you start adding to it again. And it's still going to be negative for a little while, but you're heading, you're subtracting, then you're adding. So that definite integral from 0 to somewhere is going to reach its lowest value at, if this were 20, that's the lowest value that you're going to get out of that, because at less than 20, it's still negative, but not as negative as it could possibly be. And then after 20, it's adding back to it, heading more in the positive direction. So it actually is that one. But let's check the other ones just to rule them out. B is kind of the opposite, where it's suggesting that the definite integral, that area, has a maximum there. And we just decided it's not that. It's definitely the lowest area it could be there, between here as you go there that way. So it's not that. And does it have an inflection point? We don't know anything about the second derivative. We just know that the first derivative is increasing. It doesn't tell us anything about the second derivative, so we can't really say anything about inflection points. So it's not going to be that. And D is suggesting that the function, again, the function being the definite integral, that it has no minima or maxima as you go from 0 all the way out to infinity. And we already decided it definitely does have a minimum. So it's not going to be that. And then the suggestion that the derivative of the definite integral at 20 does not exist. Well, we already decided that that's a minimum of a function, which is the definite integral. So not only does it exist, we can say it's 0. If it asks us that, we know it's the minimum, we know it's going to be 0. So it does exist. And the total answer to the question, a little convoluted again, because you have to remember what it's asking you about. It's not asking you about function g, it's asking you about the definite integral, as the upper bound is your variable. It doesn't tell you where the upper bound is, so you have to figure, how does the result of the definite integral change as your upper bound increases? And that's what it's asking there. And that's the answer we get. So moving on. Let me go back to my original page here. It is A. Number 30 is asking about Riemann sums. So what is a Riemann sum? Riemann sum is another one of those things where it is only touched on very, very briefly in a regular calculus class. And the basics of that is you have some function and you want to know the area under that function, but we haven't discovered definite integrals yet. So how do we, what's some way that we can use to approximate this? We'll say that's the x-axis. And one way you can kind of do it is you can figure out the height of the function at various points, and then draw some rectangles at regular intervals. Just pretend that each of these rectangles is the same width. And so you would have to individually calculate the value of the function at each of these x values, every y value for each of these x values, and then you add all those together to get the height of all the rectangles added together, and multiply that by the width of the rectangles, and that gives you an answer, a number that's pretty close to the area underneath here. And what actually happens in calculus class is they say, okay, if you make more and more rectangles, making them thinner, so you have, obviously the thinner the rectangles are, the better the approximation is, because the more closely it's going to match up with the original curve. And if you take it out to an infinite number of rectangles, so that they are infinitesimally thin, and then you say, well, we want to find the limit as the number of rectangles approaches infinity, that is actually how the whole definite integral function is derived. And then having done that, you use the definite integral from then on, and you never look back at Riemann sums except on a test. So what this is the kind of traditional notation here. This is a sum notation. And what this is saying is, for some value, for the value of I in the function, you're going to start at I equals 1 and go up to I equals 50, and then add all of those together. So, if you were doing this on, a spreadsheet or some program in your calculator, or taking a really, really long time to do it by hand, you would calculate this for I equals 1, I equals 2, I equals 3, all the way on up to I equals 50, calculate it out for all of those, and then add them together. That is what that notation means. So, and then it's telling us it is on the closed interval 0 to 1. So we're finding the area under some curve between 0 and 1. If we were doing the definite integral, that would be the bounds 0 to 1. That's what that means. And then what the 50 is telling us is that the row of rectangles, we're doing 50 of them. So the width of each rectangle is 1 over, divided by 50. That interval, which is just 1, divided by 50, because there's 50 rectangles. So the height of all the rectangles, the height of all 50 rectangles, times the width of 1/50th would give us that approximation of the area under the curve, which we would normally just get with a definite integral. So I already just revealed that we know it's going to be a definite integral from the bounds of 0 to 1. So it's not going to be this, and it's not going to be this. They're trying to fool you with different arrangements of the 0 and the 50 here. So which of the remaining ones is it going to be? So let's look back at this sum function. What are the parts of the function that we're getting here? So this 1 over 50 is just the width, as I discussed before, the width of all those. So that's not part of the function. That's just what we're multiplying by, because we have an interval from 0 to 1. It's 1 wide, divided into 50. So that's just a consequence of that we're doing Riemann sums. So then what we're left here is I over 50 squared. And so again, you can kind of intuit from this that the 50 comes from that we're doing 50 bars. And if you think about that, if you have some graph and you're doing 50 individual rectangles, from 0 to 1, the first place is going to be 1/50th, then 2 50th, and 3/50th as you're calculating each individual value before you add them up. Hopefully using a program or a spreadsheet or something, not doing it by hand. So basically the over 50 is also just a consequence of that we've divided it into 50 bars, and all that we're really left with is the I squared. So again, it's not, the 50, the being over 50 comes from the 50 divisions in the Riemann sum, and certainly not that one. So what we're left with is just a simple x squared. If you were doing a Riemann sum of, instead of doing a proper definite integral, if you were to do a Riemann sum of that with 50 divisions, you would write it this way because you're chopping it up into 50 individual points that you're checking, multiplying by the width, 1 over 50, and then doing the sum for values of I from 1 to 50. And this is, Riemann sums are a pain, but if you understand what goes into them, this kind of thing comes out to be pretty easy to do. And that's it for that batch of questions.